Hello, my name is Nicolas Ghandour. I am a student at the Energy and Digital System Engineering at the Polytechnic Institute of UniLaSalle, Amiens in France. And in the course of my major, I had to do a project in robotics, which was designing a car robot that is able to autonomously traverse distances.
To be able to traverse the maze on its own, the robot uses proximity sensors to tell it how far the obstacles are from the car, and accordingly it will be able to recognize in what direction the car robot should move. The microcontroller, the brain of the robot, is the Maker Nano, which is a compatible version of the Arduino Nano board and is widely used in educational robotic applications. Having its ATmega328P as its core, the Maker Nano microcontroller has 20 general-purpose input-output pins that can be configured either as analog or digital input or output, allowing the microcontroller to interface to other electronic components.
Next, we have the infrared proximity sensors, the VL61ETX, which can detect obstacles up to 60 centimeters. It is interfaced using the I2C communication protocol, which implies using VCC and ground signals to power the sensor, the SCL signal to receive the clock signal from the microcontroller, and the SPA line that allow data communication with the microcontroller.
Then we have the servo motors, the component that controls the displacement of the car robot. It's a very popular component and can be easily interfaced with the Maker Nano. And to activate it we need three signals: VCC, ground, and the PWM signal, through which we control its rotational speed.
Other components were also used, like a shield for the Maker Nano that makes connecting other components to the Maker Nano easier, as well as the wheels, the small wall placed on the front and under the car, allowing smooth replacement of the car robot and eliminating the need of two additional wheels to stabilize the robot, the power bank and micro USB cables to energize the Maker Nano board and electronic components. And finally, the 3D printed car chassis, the skeleton of the car, on which all the components are attached.
To assemble the different components, I used the wrapper, which is a wiring tool to connect the proximity sensors pins to the Maker Nano board pins. I also used screwdrivers to securely fasten the physical components to the robot's chassis. During the assembling process, the proximity sensors were first mounted on the front of the chassis, as shown in the top view. As you can see, we have three sensors: the right sensor, the middle sensor, and the left sensor. Then, the Maker Nano microcontroller, along with its shield, was securely fixed on the top of the robot using a screwdriver. Next, using the wrapper, the sensors were connected to the Maker Nano board for proper signal wiring. Moving to the bottom view, underneath the chassis, the steel ball was fixed, and the servo motors were installed and connected to the Maker Nano to control the wheel movements. And finally, a power bank was added to supply energy to the entire system as seen in the back view. Moving to the electronic part, after connecting VCC and ground to the sensors, I connected them to the shared SDA and SCL, which correspond to the A4 and A5 pins of the Maker Nano respectively. And I used the D2, D3 and D4 pins as the CE signals of the sensors, which will be used for the addresses assignment. Then, for the servo motors, after also connecting them to VCC and ground, I connected their control signals to the D6 and D9 pins. Now I will explain for you the programming part of the project. In order to program the Maker Nano board, I used Arduino Integrated Development Environment, which is a very useful tool for simple robotic applications and projects. For example, here I can very easily select the board I'm working with. Here we can also search for libraries, install them and include them into our project or program. In the tools, most importantly, we have the serial monitor, that is a debugging tool that helps the programmer to detect errors and problems in the code. So now I will explain for you my code. First we have some declarations, like here we declare the sensors, we declare some constants, some parameters. Here we have the function that controls the motor's speed, the left motor and the right motors, and we have different actions. We can either move forward, move backward, and all of these actions call the same function with different arguments. Next, we have the setup function, which is executed only once at the beginning of the program. In this function, we do initializations and configure pins. For example, for the sensors, for our proximity sensors that are interfaced using the I2C protocol, which means they share all the same SDA and SCL signals, we need to assign them different addresses to distinguish them. And in order to do so, we first turn them off, then we turn only one on and do the proper initialization, and we repeat the same process with the second and third sensor. And finally we have the loop function, the main function of the program, that is executed an indefinite number of times as long as the board is connected to a power source. First we will read the sensors data that will tell us the distance of the obstacles near the car and in front of the car. And accordingly we have three major cases. First, whether the car robot is on a sharp turn. Second, whether the car robot hits the front wall. And third, whether the car is on the long road. For the first case, what we will do is detect the direction of the sharp turn. For instance, if the sharp turn is on the right, then we will move right sharply. And similarly, if it was on the left, we will move left sharply. Now for the second case, if the car hits the front wall, we simply move backward, and of course we stop the motors for a certain delay to stabilize the sensors. As for the third case, we keep moving forward while taking care of the direction of the car. And what I mean by this is that whether the car is getting nearer the left or the right wall. For example, if it's getting near the left wall, we need to move slightly right. And similarly, if it gets near the right wall, we need to move slightly left. And the default case is that we keep moving forward. During testing, the robot exhibited two main issues. First, it sometimes entered a continuous back and forth motion when encountering obstacles. Video analysis in slow motion revealed a timing error, which was resolved by increasing the backward delay to allow accurate distance measurement. Second, occasional incorrect sensor readings caused the robot to make wrong turns. After testing each sensor manually, the problem was traced to an instability of the front part of the car robot, which sometimes tilted and caused the one sensor to abnormally read small distances. To solve this problem, I firmly secured the mount using cables. Although this did not eliminate the problem, it greatly reduced false detections. The objectives set for this project were successfully achieved. Through this project, I strengthened my skills in electronics, microcontroller programming, and robotic systems design and troubleshooting methodologies. This project also highlighted the importance of dividing the work into several parts and subparts that will make problem solving faster and more effective.